electric potential and capacitance. In this chapter, we are going to learn about electric potential and capacitance. Electric potential measures the ability to perform work on a charge, whereas capacitance measures the ability to store the charge. About these two concepts in this chapter we are going to be studying. So the first one is electric potential and its relation with the electric field. Electric potential introduction. What is meant by electric potential? Let us observe here no charge is located. Means electric field in this space is 0. Now I am going to place a charge capital Q at point O. Once a charge is placed at this point, around this charge some electric field is produced. This is a positive charge, hence the electric field due to this positive charge along this direction is directed like this. This is electric field direction. Let us assume the electric field is limited to this region. Now, any point which situates outside this region is said to be at infinity with respect to plus capital Q charge. Now, at this infinite point, a charge plus Q0 unit positive charge or test charge is placed. Now, I want to move this charge from infinity to this point. This point is, let us consider P, situates at a distance R. To move this Q0 from infinity to P point, we have to do some work. Why? Because if the charge once, this Q0 once comes inside the field, it is repelled by this plus Q charge. But you want to bring this Q0 from infinity to R distance to P point. For this, we have to move the charge Q0 against the electric field. We have to do some work. That work done to move unit positive charge from infinity to given point inside the electric field against the field direction is called potential at this point. Potential at P point is defined as amount of work done to bring this Q0 from infinity to P point against the field direction. You want to move this Q0 along this direction, opposite to field direction. There exists a repulsive force between Q and Q0. But you want to move this charge Q0 to P point. For that, we need to do some work. That work done is the electric potential at this point. Now, what is the electric potential? How the electric potential is defined? Electrostatic potential at any point in an electric field is the amount of work done in bringing a unit positive charge from infinity to that point. At which point we are going to find the electrostatic field. To that point from infinity to. a unit positive charge is moved. To move that unit positive charge from infinity to given point, some work has to be done. This work done in bringing a unit positive charge from infinity to that point is called electric potential. It is numerically equal to work done. Work done is also potential energy. Work done are electrostatic potential energy per unit charge. That means electrostatic potential V is equal to work done W per unit charge by Q or Q naught. Unit charge is taken as plus Q naught. So work done to move the unit charge. Electrostatic potential is a physical quantity which determines the flow of charges from one body to another body. Always charges flows from high potential to low potential. Charges flows from high potential to low potential. Hence, electrostatic potential is a physical quantity which determines the flow of charges from one body to another. Now, electrostatic potential governs the flow of charge between bodies. Why? Because it flows from high potential to low potential, and it is degree of electrification of a body. Up to what extent the body is electrified, that is measured by using its potential. That's why the electric potential is degree of electrification of a body. Now, V equal to W by Q, work done per unit charge, or potential energy per unit charge. Which potential energy it is? This is electrostatic potential energy per unit charge. What is the SI unit of this potential? V equal to W by Q. W measured in joule, charge measured in coulomb. So, electric potential SI unit is joule per coulomb. Also called it as volt. Joule per coulomb is also called as volt. What is its dimensional formula? Dimensional formula is, will do V equal to W by Q. W is the work done, M L square T power minus 2 by charge. From the current definition, I is equal to Q by T. Q is equal to IT. I stands for current. Current dimensional formula is A. T time, capital T. That means electric potential dimensional formula M L square T power minus 3 A inverse. This is the dimensional formula of electric potential. Next one is electric potential difference. What is meant by electrical potential difference? Here, a charge is placed at here at point O. That charge is plus Q charge. Electric field is limited to this region, and along this direction, the direction of electric field is this direction, E bar direction. Now, a charge is placed. Which charge? Plus 1 coulomb charge, called it as test charge, is placed at infinity distance To bring this unit positive charge to a point P at a distance smaller from the plus Q charge, we have to do some work. That work done we called as electric potential. Now, what is the electric potential difference? The electric potential difference is the amount of work done to move unit positive charge from one point to another point inside the electric field. Let us consider this is the electric field produced by this plus Q charge. Now, inside the electric field, 2 points are there. This is the 2 points. Let us consider A, B. To move this plus Q0 charge from infinity to A point, the work done is taken as WA. To move the Q0 from infinity to A point, amount of work done is WA. Similarly, to move the Q0 from infinity to B point, the amount of work done is WB. Now, identify. In this WA and WB, which one is greater? WA is the work done to move plus Q0 from infinity to A point. WB is the amount of work done to move plus Q0 from infinity to B point. Now tell me, to plus capital Q charge in those points A and B, which one is closer? The closer one is B point. Now, to move this plus Q0 from infinity to A and B, we have to do more work to move this Q0 to B point compared to A. Means WB is greater than WA. There is some work difference between A and B points. Now, the potential at A point, VA, is equal to, formula is work done by time WA by Q0. Similarly, potential at B point, WB by Q0. Here, WB is greater than WA, which implies VB greater than VA. Potential at B point is greater than potential at A point. Means VB is greater than VA. That means there exists some potential difference between the 2 points A and B. That is dV, potential difference. dV is equal to potential at B point minus potential at A point. This is the definition of potential difference. How we define the potential difference? Amount of work done to move unit positive charge from one point to another point inside the field against the field direction. I want to move the charge from A to B. So amount of work done to move unit positive charge from one point to another point inside the field against the field direction. That we define as electric potential difference. Now, statement of potential difference. Potential difference between any 2 points in an electrostatic field is defined as the work done to transfer unit positive charge from one point to another, or potential difference is the potential energy difference between the 2 points per unit positive charge. That is also defined as potential difference. dV equal to dW by Q, or dW is du, change in potential energy, by Q. Observe here, these two are at different potentials. Potential of the first sphere is negative, high potential, and the second one potential is 0. Observe here, 0 potential. Now these two are connected with some conductor. Then what happens? Charges are flows from one conductor to another. Charges flows from one to other until the potential of the two spheres become equal. The potential of two spheres are become equal means the potential difference between these two bodies is 0. So first, if there is potential difference between the two spheres, once you connect in them by a conducting wire, bulb glows. Why? Because potential difference is there, and charge flows between them until the potential of both the conductors becomes same. The potential difference between the two conductors becomes 0. Means charge flows between the 2 points until both the points come to same potential. Now, this one is one more example. Always electric field directed from high potential to low potential. From positive plate to negative plate, electric field is directed. Now, electrostatic potential due to positive point charge. Due to single charge, at a given point, we are going to calculate the electric potential. For that, let us consider a charge Q is placed at here. Now, we are going to find electric potential at a point which is situated at a distance R. Now, the P point is situated at a distance x from the Q charge. At this P point, a Q0 charge is placed. On this Q0, due to this Q charge, some force is acting. What type of force? Repulsive force, electrostatic repulsive force. That electrostatic repulsive force try to push this Q0 away. Let Q be the point charge, P be the point of observation in its electric field. Let a unit positive charge plus 1 coulomb placed at P point in the electric field produced by this Q. This Q0 is placed inside the electric field which is produced by this Q charge. Let us observe. So here, if Q0 is placed at this point, from Q to Q0 is situated at x distance, there should be repulsive force between Q and Q0. That repulsive force, first we are going to calculate. The electrostatic force between point charge, this is point charge plus Q, and Q0 is unit charge. Unit charge means its charge is 1 coulomb. So what is the force between these two? So force between the two charges F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. That is the formula. Here Q1 is plus Q, Q2 is 1 coulomb or Q0 separated by x distance. Hence, F is equal to 1 by 4 pi epsilon naught Q2 is 1 by distance square, x square. Now, F equal to 1 by 4 pi epsilon naught Q into 1 is Q by x square. Equation number 1. Consider small amount of work for displacing this Q naught from A to small distance dx against the electric field. We want to move this Q naught from A to B through a distance dx against the electric field direction. Electric field is directed along this direction. Now we are going to move the Q naught from A to B through what distance? Dx. The amount of work done is small. Why? Because small distance we are displacing. So that work done is dW. Here the force acting on Q naught is directed along this direction. The displacement is from A to B along this direction dx. So F and dx both are making an angle 180 degrees. Then dW is equal to F dot S. F dot product means cos theta. What is theta here? 180. F this value. How much distance we are going to displace? Through small distance dx. Then dW is equal to F dx cos 180. Cos 180 is theta is what? 180. Cos 180. Cos 180 is minus 1. Hence dW equal to minus F dx. This is the amount of work done for small displacement. But actually, we want to move this Q naught from infinity to R distance. To get total work, we have to integrate this equation within the limits infinity and R. So, total work done to move the Q naught plus 1 coulomb charge. Q naught is what? Plus 1 coulomb charge. From infinity to R distance P point. To get that work, we have to integrate this equation. Integral dW is equal to minus integral. What is F value? 1 by 4 pi epsilon naught Q by x square into dx. What are the limits? We are going to move from infinity to R distance. Infinity to R distance. The work done is W is equal to minus Q by 4 pi epsilon naught constant 1 by x square dx I am writing as x power minus 2 dx. Integral limits are infinity to R. W equal to minus Q by 4 pi epsilon naught integral x power n dx form. X power n plus 1 by n plus 1. So here n is minus 2. So x power minus 2 plus 1 by minus 2 plus 1. What are the limits? Infinity to R, which is equal to minus Q by 4 pi epsilon naught x power minus 1 plus minus 2 plus 1, that is minus 1, by minus 2 plus 1 minus 1. Limits are infinity R. Q by 4 pi epsilon naught minus plus x power minus 1 is taken as 1 by x. Limits are infinity and R. Now I am going to substitute these limits. W is equal to 1 by 4 pi epsilon naught. Here Q by 4 pi epsilon naught into first upper limit 1 by R minus lower limit 1 by infinity. 1 by infinity value is 0. Hence W is equal to 1 by 4 pi epsilon naught Q by R. This work done stored as electric potential. We know that work done on unit test charge is called the electric potential. Hence, V is equal to 1 by 4 pi epsilon naught Q by R. This is the expression for electric potential due to point charge. V of R, potential at a distance R from the point charge, which is 1 by 4 pi epsilon naught Q by R. Electrostatic potential due to point charge is now V as a function of R at a point which situated distance R from the point charge is equal to 1 by 4 pi epsilon naught Q by R. Now, electrostatic potential due to multiple charges. Here, electrostatic potential is work done per unit positive charge. Work done is a scalar quantity. So, electric potential is also scalar quantity. Due to that, to find the electric potential, we have to use algebraic sum of the individual potentials. Why? Because potential is a scalar quantity. Consider a system of charges Q1, Q2 and so on Qn are situated at position vectors R1 bar, R2 bar, R3 bar relative to some reference point origin. At this point, V1, V2 up to so on Vn are the potentials due to these charges Q1, Q2, Q3 and so on Qn respectively. P point. Q1 is situated at R1 distance from P point. Q2 is situated at R2 distance. Q3 is situated at R3 distance and so on. So like this. From P point, Q1 R1 distance, Q2 R2 distance, Q3 R3, Q4 R4 and so on. Qn is situated at Rn distance. What is the potential at P point due to all these charges? Due to multiple charges. That is nothing but algebraic sum of the individual potential due to individual charges at that point. Since potential is a scalar, the above potentials are added at point P. Just addition. So net potential is sum of the individual potentials. V is equal to V1 plus V2 plus and so on Vn. So V1 value. Potential at P point due to Q1 charge which is situated at R1 distance. V1 equal to 1 by 4 pi epsilon Q1 by R1. Similarly, V2 is the potential at P point due to Q2 charge which is situated at R2 distance from the P point. That is 1 by 4 pi epsilon Q2 by R2. And due to Q3 charge situated at R3 distance 1 by 4 pi epsilon Q3 by R3 and so on. Due to number of charges. So V is equal to 1 by 4 pi epsilon getting common Q1 by R1 plus Q2 by R2 plus Q3 by R3 and so on Qn by Rn. That is the potential at the given point due to multiple charges. Due to all these charges at this point, potential formula is this one. V equal to 1 by 4 pi epsilon Q1 by R1 plus Q2 by R2 plus Q3 by R3 and so on. So, 1 by 4 pi epsilon naught sigma I equal to 1 to n. Number of charges are there, then sigma I equal to 1 to n. Summation is there, that's why sigma. Qi by Ri. This is the electrostatic potential due to multiple charges at this point. Due to system of charges at this point potential expression is this one. V equal to 1 by 4 pi epsilon sigma Qi by Ri where I is 1 to n. Based on potential one problem. A sphere has a charge 50 coulomb. The absolute potential at a point. The distance of the point is given as 10 power minus 12 meter from the sphere is. Options are 4500 volt, 45 into 10 power 23 volt, 4.5 into 10 power 23 volt, 4.5 into 10 power 24 volt. Solution. Potential due to point charge formula is V equal to 1 by 4 pi epsilon naught Q by R. The value of 1 by 4 pi epsilon naught is 9 into 10 power 9 into Q, charge value 50 by distance 10 power minus 12. This 10 power minus 12 goes to top as plus 12, which is equal to 4.5 into 10 power 23 volt. Correct option is third option.